So what I wanted to spend the rest of the time discussing is the InSight mission. And this actually is launching a week from Saturday. May 5th is the opening of the launch window. And so I wanted to give you a bit more detailed overview of this mission than what we've done in the past. Just to orient you here, the spacecraft is modeled after the Phoenix mission, which landed on Mars in 2008. It was a polar mission, or an Arctic explorer, I guess you'd say. Landed up near the Arctic Circle on Mars and discovered with its instruments that there was permafrost just under the surface. So anyway, this is built by Lockheed Martin here in Denver. And so they've taken the successful design from Phoenix and put different instruments on it. And so InSight stands for Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport. And the key to a good mission is a good acronym. So they really had to stretch hard to get that, but they did it. So that's the story. And the basic mission for InSight is to examine the interior of Mars, which is something that we've never adequately done before. We've done a lot of surface geology. The MAVEN mission, the most recent US orbiter, is studying the atmosphere of Mars, but we don't know a whole lot of detail about the interior. And so this really is the basic goal, is to understand how Mars and the other rocky planets formed, and to really understand the interior of Mars. And we're going to do that with this mission. There's a seismology experiment. There's a heat flow experiment measuring the temperature gradient under the surface, how different the temperatures are as you proceed downward, and then tracking of the rotation of Mars to help understand the interior as well. And so back when the planets were forming, there are a number of steps here. There's lots of these little sort of proto-planets that collide with each other, and they start building up a planet, and all of the collisions release a lot of energy, as well as lots of radioactive elements in these protoplanets. And so the interior starts to heat up as the planetary body grows, and it eventually melts on the interior, and then stuff happens. So that's where, as the planet is primarily molten, all the heavy stuff, the iron and the nickel in the case of the Earth, and things like that, sink toward the center of the planet, and you get, it's called differentiation of the planet. And then eventually you end up with a planet that has a core and a mantle, which has a distinct composition, and then the sort of the scum that floats to the top is the crust. And so here's where InSight is really specializing, is what happened here, trying to determine the details of the formation of Mars. And so just in comparison, we've done 100 years or more of seismic surveys of the Earth and lots of other geologic examinations of the Earth. So we know really well what the interior structure of our Earth is, and it's got a solid iron core, and then there's a liquid outer core, and then a mantle with multiple layers, and then somewhere between 5 and 50 kilometers of crust, depending on whether you're under an ocean or on a continent. And so that's the basic details of the Earth. But when we look at Mars, we know it has a crust. That's what we see. And We think it has a mantle. It certainly should, and the gravity studies would indicate that it's separated that way. And the gravity studies also indicate that it has a core, but we don't know if that core is solid or if it's liquid, and we don't know how big it is. And ditto, we don't know if the mantle has multiple layers. And so that's what we're going to try and find out. And so the key to doing this is, instead of just measuring the gravity field as a spacecraft orbits near the planet, is you actually need to have seismic experiments attached to the surface. And the first time we tried to do that was with the Viking landers back in 1976. But on the Vikings, the seismometer was actually on the lander itself, on the top of the lander. And so it relied on vibrations being transmitted through, through the legs, the landing legs, and then being picked up by the seismometers. So on one of the two Vikings, the instrument just failed completely. On the other, it became very obvious very quickly that what they were measuring was the lander itself. If you got a gust of wind, the lander would vibrate a little bit. Every time you moved a mechanism, and there were lots of mechanisms on board, it just totally swamped the seismic signal. So it really wasn't a useful experiment. And okay, I'm not sure why. There we go. And so come forward finally to 2018, and InSight will have the capability with its little robot arm to reach out and put the seismometer down on the surface so that it's totally decoupled from the spacecraft. And it's a very, very sensitive instrument. And so there's actually three main parts to the payload. There's the seismic experiment, there's a heat flow experiment, which will actually burrow about 5 meters deep if everything works well. And then there's a radio experiment, which will very accurately, within about 10 centimeters, be able to determine the distance between the Earth and the landing site on Mars and measure how Mars is rotating around its axis or about its axis. And so those are the basic parts of the package. And then there's a robot arm here, which helps facilitate placing both the seismic experiment and the heat flow experiment. And this is just a basic model of what a seismometer is. Imagine a little spring with a weight on it. And if you vibrate the mounting part of this spring, the weight starts vibrating as well. And it turns out the design of this seismometer, it can measure vibrations about half the diameter of half the radius of a hydrogen atom. And that's very, very precise device. And so there's lots of different pieces to this, but you can imagine how complicated it is to put one of these together. And in fact, the seismometer, the original seismometer failed. This whole sphere is under a very low vacuum, and or high vacuum, I guess you'd say. It's a very good vacuum, and they couldn't hold the vacuum. And it needs that because if there's any atmosphere in the enclosure, then just the motion of the molecules in the gas inside can cause noise. And so originally, InSight was scheduled to launch in March of 2016, and the instrument wasn't ready. And they actually spent a lot of time working on it, rebuilding it, and it still wasn't ready. And so they ended up postponing the launch 26 months until the next opportunity, which is opening next week. And so that's what the seismic experiment looks like. Lots of, there's a very long tether connecting it to the spacecraft. A second part of it is this, which is the wind and thermal shield, and it's sort of like a chain mail skirt. This whole thing gets placed over the seismometer to protect it from wind gusts and to help stabilize the temperature. And we'll see an animation of that in just a second. And so what are they going to be looking for on Mars? We don't know for sure that Mars has Mars quakes, but there's a variety of signatures that we will be looking for. One is if you have faults on the surface, then if the faults actually slip, that causes a Mars quake, and so we'll be able to measure that. We'll be able to measure the tides as the two Martian moons orbit overhead, and so that provides just a little flexing of the crust, so that should be possible. We expect to see multiple times a year impacts where meteorites are hitting the surface, and this is an example from orbit between June of 2008 and August. This splotch appeared, which is an impact. And so far in the Mars Reconnaissance Orbiter mission, we've detected something approaching 100, I believe, discrete impacts. And so those should provide a good signal. And then the final thing is we'll be able to see atmospheric storms and waves propagating overhead. And so all of those should be detectable. And so this is just a visualization of if there is a Mars quake or an impact or a slipping of a fault, how complicated the waves are that travel through the interior of the planet. But the point is, if we're sitting down here and we can actually detect this and record all of that, then there is hope that you can actually decipher this. And so this is just a schematic of how all these different waves play together. So here's the Mars quake, whether it's an impact or a fault or whatever. Here's our spacecraft. And the first thing, the fastest waves that get it go straight through the interior of the planet. So that helps us measure the mantle and the core. The second ones travel along the crust. And so there's one set of them come this way, one set of them go completely around the planet, and then with time, they keep circling the planet until they die off. And so that gives you, 4 different signals that you can plug into the models, and ultimately you come up with here's where it was, and here's how strong the event was. So that, just one aside here, in testing here in Denver when they were getting ready to install the seismometer on the spacecraft, there was sort of noise in the signal, and ultimately they determined that was waves crashing on the Pacific coast of the United States. And so they were actually able to see the signature of ocean waves hitting California. Okay, and so here's the heat flow experiment. In many ways, this is even more novel than the seismometer. So this gets set out on the surface, and then it's got a little percussion device that it's like a pile driver that keeps hammering, and it slowly, over the course of several weeks, pounds a probe about 5 meters down below the surface. And it's got temperature sensors every 35 centimeters along this tether that's left behind. And so that allows it to determine differences in temperature with depth. And then they also have heaters on the end of the probe. And so they can say, we just heat it up to a certain amount, and how long does it take for that signal to, or signature to travel up the probe. And so that tells you a lot about the subsurface structure, and it also tells you how much heat is escaping from the interior of the planet. And so this is a view of the probe, and here's the, let's see, the mechanism, the hammer mechanism. So there's a weight here, and it keeps raising the weight, and then it's got a spring that pops it down, and it moves a little bit downward, and it keeps it up until it's as deep as it can get. Okay, and then the final experiment is this precision radio tracking experiment. And so the key to this is they've got very stable radio receivers on the spacecraft as well as transmitters, and they can transmit signals back and forth between the Earth and Mars, and that gives them the ability to determine how far away Mars is, how far away the lander is on Mars, rather, and how this changes with time. And so the basic part of this is called nutation, which is a slight wobble in the spin axis of Mars. And so they're going to be able to measure this, and that is all related to the interior structure. If Mars has a solid core versus a liquid core, the signal will be very different. And so that'll help a lot. Okay, so this is the spacecraft as it was being prepared here at Lockheed Martin. And the overall view of the mission here is it's going to fly a very similar profile to what the Phoenix lander did. And so here's our launch window. It opens May 5th. It runs about a month until June 8th. And each day they have about 2 hours that they can launch in. So every 5 minutes in that 2-hour period, they have a launch time already built in. And so this is going to launch from California at Vandenberg Air Force Base, regardless of when it takes off, irregardless, I guess is the right term. It's going to land on November 26th, which is the Monday after Thanksgiving. And so then for the next 2 months, they'll work on deploying the instruments. And then they've got about 1 Mars year to gather all of the science. And so that gives them a nominal mission duration of about 2 Earth years, so into November of 2020. And so one of the unique things of this is actually the first time that a planetary mission has launched from California. And the original reason for that back in 2016 is there were scheduling problems at Kennedy Space Center or Cape Canaveral. And so since the rocket they're using, the Atlas V, actually has excess capacity for a spacecraft of this size, they were able to launch in sort of a polar trajectory from California and still make it to Mars. And since they'd already designed that, everything about a launch from California, they adopted the same mission profile for the 2-year later mission. And so it really does help free up the schedule in Florida, because the planetary missions, since they have a very discrete length of time that they can possibly launch to Mars, they take priority over everything else. And so potentially, if you had delay after delay after delay from weather, say, then you end up bumping all of the other missions. And right now, there's typically 2 or 3 or 4 launches a month happening from Florida. And so that makes for a very busy schedule, and this helps free that up. And this is just a graphic of the path that the spacecraft follows. So here's the blue orbit is Earth, the red is Mars, and here's after launch, the spacecraft basically runs into Mars. And so here's where they're going to be landing. It's very near being multiple hundreds of kilometers from the Curiosity landing site. It's in a volcanic region called Elysium. It's a very flat region, and this is just a topographic map of that. And so here's the landing site, and this is a close-up view. And so at the opening of the window, this would be the target area, the orange ellipse. By the close of the window, we'd be targeting the white ellipse, but all of these, basically the center is going to be right there. And this was chosen by high-resolution imaging of the surface in this region to look for a surface that has a minimal amount of rocks, very flat, and what you don't want is to land in the middle of a boulder field where you're going to have trouble finding spots for both the seismometer and the heat flow experiment. So here's how the approach to Mars will happen. This is called the 7 minutes of terror. And it takes about 7 minutes from when the spacecraft hits the upper atmosphere until it's on the surface. And so first it uses its heat shield to slow down, and it slows to about 2,000 miles an hour, and pops a supersonic parachute, drops its heat shield, and when it's just a couple kilometers above the surface, it drops down, it fires its descent thrusters, and slows down to about a kilometer an hour, and drops down under the surface. And then in about 16 minutes after launch, they deploy the solar panels, which are folded up sort of like Chinese fans. And at that point, they're ready to go. So this is an animation then of, after several weeks of them deploying the seismometer and the heat flow experiment. So this is the seismic, the basic seismic experiment. Here's the tether that connects it to the spacecraft. And so they spend a lot of time characterizing what's in front of the lander and determining exactly where they want to set that down. And then once they've got it on the surface, the next step is to cover it up with the wind and thermal cover. To deploy the heat flow experiment. And then over the course of a month or so, the heat flow experiment burrows into the surface. And so, pardon me?
What if they have land on a much rockier place and have rocks everywhere? How do they know that seismic is going to land on a flat surface?
Well, they have lots of, they've got a couple of cameras that they're going to spend a lot of time looking at what's available within reach of the arm. And so, unless they get very unlucky, there should be at least an open space. The bigger worry in that case is if there's lots of rocks in the subsurface. And the heat flow experiment, if it doesn't make it at least, I think, 1.5 meters below the surface, then it will not be able to do its experiment. And once they've placed the heat flow experiment and started, the pile driving or the burrowing, they can't remove it. So they can, up until they actually start operating these things, if they get it down on the surface and decide this isn't a good place, I'd rather move 1 meter over this way, they can do that until everything is completely assembled and ready to go. So the final thing, and this is just sort of a cool experiment, is this thing called Marco, which is, there's going to be 2 small CubeSats launched with the InSight spacecraft. And the way this works is, so here's our launch from Earth, here's the path to Mars, the descent onto the surface, but on the bottom of the upper stage of the Atlas V, there's actually, 2 small spacecraft that each weigh about 30 pounds, and they're going to be deployed on their own trajectory, and they will fly past Mars and if everything works, they'll be flying overhead as the InSight lander does its entry, descent, and landing. And so they'll be able to act as radio relays for the landing sequence. And so they're not the primary way of doing that. The Mars Reconnaissance Orbiter will be orbiting overhead as well. But this is an experiment to see if these very small, inexpensive spacecraft can actually do a job like this. And so here's a graphic of what this looks like. It's got little solar panels, it's got an antenna, and it's 2 autonomous spacecraft. And so this would be them flying overhead as the InSight lander sets down. And so that's just an artist concept of how those would look flying by. And so where are we right now? So here's the Phoenix lander. This was about 10 days ago or so. So the lander is here. This is the cruise stage of the spacecraft. Here's the heat shield, which plops on top of there. And there's the whole assembled spacecraft ready to go. And there's the payload fairing. So they've encapsulated it in the payload fairing. Just in the last couple days, they installed the payload on the top of the Atlas V, and they're ready to roll. So the time of day, unfortunately, isn't very program friendly, shall we say. So it's up to you guys to get up and watch NASA TV at 5 o'clock Mountain Time. So the launch window extends from 5:05 to 7:05 a.m. Mountain Time on the 5th. Every day, if it slips, it gets earlier by a few minutes. But certainly this will be covered on NASA TV on their website, or if you have either DirecTV or Dish Network, you can get it directly. And we'll certainly be replaying this in Space Odyssey once it takes place. And so we'll hopefully be talking about a successful launch at 60 Minutes next month.